Right. So this is day 2 of properties of matter. I think everyone hears me, right? Right. At the last day we discussed up to wires in series. I think all you have learned up to that, right? Wires in series. I discussed up to that. So today I have to discuss about wires in parallel, wire systems in parallel, and something about like temperature and Young's modulus. Then potential energy due to the Young's modulus. Potential energy due to the Young's modulus. So those are the topics I will be covering today, and I will be doing questions as well on the tute. Okay, right. Write down the topic wires in parallel. Okay, write down usually today I will finish all the theory parts from this lesson, right? Plus the questions. Okay, write down usually wires have equal lengths. Wires have equal lengths when they are parallel. Then write to the same line, when a load is applied to it, extensions also becomes same. To the same line, right? Then tension of each wire it should be a sum of tension, right? SUM, sum of tension of each wire is equal to hanged load. I'll be going through the theory parts a little quicker because I'm planning to do many questions from this, right, today. Right, so wires in parallel means, so if you have two wires like this, you can hang a load from this. So you can see, usually we take these lengths of wires to be the same, right? Then due to this load, what happens is both wires extends. Let's say, then the extensions also is same in both wires, because we need to keep this rod horizontally all the time. We are not solving problems like inclined rods, right? Usually we take this rod to be horizontal all the time. So you can see lengths are the same. Then the extensions of each wire also we take to be same. Then what happens is, let's say the tension of this is T1 and the tension here is T2 and the weight is W. So in a parallel connection, what happens is sum of these tensions is equal to the weight. I mean the weight of the object hanged from these wires. It doesn't necessarily need to be two wires, it can be many wires, right? This is for just an example. So that whole thing is explained in those sentences above. Just draw this one quickly, draw both quickly. Right, so I'll further explain this one using a question. Okay, using a question. Write down Q1 Q1. Write down ends of a light rod, ends of a light rod, ends of a light rod with length, ends of a light rod with length 1 meter, 1 meter are hanged by two wires, are hanged by two wires, are hanged by two wires, each wire with same length, each wire with same length and cross section, with same length and cross section. Then one of the wire is made of steel, one of the wire is made of steel and another with copper, and another with copper. A load is placed on the rod, so the rod stays horizontal, so the rod stays horizontal. Write down, find the extension on each wire, find the extension on each wire. Right. Okay, so draw a sketch, try it yourself, right? I'll be explaining, but try it yourself first. Draw a sketch first. Length and cross section of wire, length and cross section of wire is same, so I'll just put LA. Then what we do is we have to place a weight on the rod. So we place this weight on the rod after extension as well. The rod will remain horizontally. It doesn't incline like this, right? One side doesn't go like this. It will remain horizontally. So what they ask is, where should you place that? Where should you place the rod in order for that to happen, right? What they ask is position of the weight. There's a precise position, so the rod will be horizontal all the time as it extends downwards. So these are the tensions in wires F1, F2. So what they ask is this distance x. Length of this rod is 1 meter, right? So this length is 1 minus x. So all you have to do is you just have to find simple x. Okay, you can complete the image. You know, whenever you have to find a distance, you have to think about moments. You have to think about moments, right? Because that is the only place where distances and forces are involved. So what I'm going to do is I'll just take moments around O. moments around O. Right, so this is F1 times X, perpendicular distance. From W there's no moment, because it just goes, there's no distance to W, right? But to other one, minus F2, distance is 1 minus X. So this is equal to 0. F2 times 1 minus X, it is equal to 0. So F1 X equals F2 1 minus X. So we got something like that. Then I can write cross multiplying F1 divided by F2 equals 1 minus X divided by X. So still we didn't get any answer there. So the goal is to find simple X. Simple X means the position of the object to be placed. Right, so what can we do? We have to find this ratio, F1 divided by F2 ratio. So at the last class we discussed this one, right? FL over AE. FL over AE. YAE divided by L. Okay, so this is, so we know both wires have the same cross section and length, and the extension also is the same. So when you divide, you write this equation 2 times and divide those equations, you will get rid of A, E and L. So what happens is F1 divided by F2 is equal to Y1 divided by Y2. I think you understand that, right? So these terms cancels off when you divide, because those terms are constants for both wires. So what happens is F1 divided by F2 is equal to Y1 divided by Y2. Y1 divided by Y2. So here the Y1 is it copper or what? Here, first wire. Yeah, it's steel, right? It's steel. So in the note at the last class, I gave you the Young's modulus, value of Young's modulus. That value is given by, you don't have to remember that value. That value is given on the paper. So for the steel, value is 2 times 10 to the power 11. Other one is copper. For copper, it is 1.2 times 10 to the power 11. Now you can find F1 over F2. So that is 2 divided by 1.2. So that is 20 over 12, 10 over 6, 5 over 3. Now you can plug this one here, 5 over 3. F1 over F2 is 5 over 3. Then just plug it here, 1 minus X divided by X. Cross multiply, 5X equals 3 minus 3X. Take it to this side, 8X equals 3. Then X equals 3 divided by 8. 0.2 0.375. 0.375. So that is where you have to place this weight, right? That's what we found. So from this question, you should understand all the theory parts. This is like this is the maximum level they can ask from this one. If you understood that and take down the question, send me a thumbs up, right? If you have any problem with that, if you have any issue, problem with the question, with the way this is done, send me a text. Okay, so you have to try this one again. Right, so we'll discuss more questions on this part when we discuss the questions on the tute. Okay, then write the topic. Next topic, elastic potential energy. Next theory part, elastic potential energy. Elastic potential energy. Okay, so the elastic potential energy is when you apply a force on an object, or let's say like a wire, its shape changes, right? When you apply a force, external force, its shape changes, and that force, that change of the shape is stored as energy in that object. So once you release the force, that object takes the original shape. We discussed those stuff at the last class. Okay, so when you like push a rubber ball, let's say rubber ball or something, its shape changes. So the work we did to change the shape is stored in the rubber ball as the elastic potential energy, not gravitational potential energy. It is elastic potential energy, right? So we have some equations for that. Mainly we are talking about rods and wires here, but this is applicable for any shape as well. For the understanding, we are only talking about wires here, right? Wires and rods. Right. Write down when a force is applied, on a wire, when a force is applied on a wire, as the force increases, from 0 to capital F, its extension increases from 0 to simple e. Okay, so we can show this in a graph. Let's say you have a wire, and if you increase the force from 0 to F, what happens is the wire extends, right? Wire extends by E. So that is that extension happens proportionally. So this is a linear graph here. So it increases from 0 to E, and the force increases from 0 to F. So if you need to have an extension of E, you need to apply a force F. That force is gradually increases to F. Then this is a linear combination, right? So we know that so this is a force distance graph. Area of a force distance graph gives us the energy. So the area of this graph is equal to the gravitational potential energy, elastic potential energy is stored in the wire, right? Okay, just draw this graph quickly. Draw the graph quickly. Okay, write down area between graph and simple E axis gives the potential energy. gives the potential energy. So below that, right, P is equal to what? 1 over 2. So this is a triangle, right? So this side length F, this side E, 1 over 2 F times E. So that's the area of that triangle. Take it down. So this is how we find the potential energy stored in a wire or a rod. Then write, since F equals Kx, sorry, Ke. Since F equals Ke, you learn this in mechanics, right? F equals Ke. You can substitute this thing here. Then what do you get? P equals half F means Ke times E. So you get the another equation. So I have to remember these equations. P equals 1 over 2 Ke squared. P equals 1 over 2 Ke squared. You learned these equations earlier as well, right? In mechanics. So those are the two equations that you can find potential energy stored in a wire. Potential energy is stored in a wire. Right. If you took that down, write this down. Consider when force applied on a wire increases from F1 to F2. From F1 to F2. Comma, its extension increases from E1 to E2. Extension increases from E1 to E2. Okay, so this is what happens. If you want, you can label this axis as F, right? This axis as E. You are free to change the axes, but you have to remember all the time the area should be the area between E axis and the graph, not F and graph. It's always E axis and the graph. Okay, so here what this is, extension increase from E1 to E2. So the forces increases as the forces increases from F1 to F2. When you apply a force that increases from F1 to F2, extension of the wire increases from E1 to E2. So what is the energy required to do this? Energy required to do this? It is given by this area, right? Always the area between graph and extension axis. So it should be this area, right? So how do we find the area of this part? Here they are not asking the energy from the beginning. I mean, when the extension is 0, they are asking somewhere once the extension is increased, right? Not from the 0. So how do we find the area of this graph? So we need to find the potential energy stored in this case. So the area, this is a trapezium. So F1 plus F2 divided by 2. So those are the two lengths, two heights, F1 and F2 divided by 2 times E1 minus E2, this length. E2 minus E1. So from this one you can find potential energy is stored. So when a case like this, you cannot apply half x k squared, right? Just remember that you always have to deal with that area, the area between e-axis and the graph. Okay, take this graph and write this equation. Only thing you have to remember is you always have to consider the area of the graph, e-axis and the graph. First recording is available, right? I'll give you that later. Just for now, just follow this one, right? Okay. Then write another theory part topic: elastic potential energy. Elastic potential energy in a unit volume. Elastic potential energy in a unit volume. Energy in a unit volume. So how do we find the elastic potential energy? Unit volume. Unit volume means a unit volume of the wire, meaning per cubic meter of the wire, or per cubic centimeter of the wire, or it can be a rod as well, right? So how do you find the in a unit volume means, let's say this is E dash. So that E dash is equal to what? Elastic energy divided by volume. Volume of the wire. So the elastic energy we found using this equation, half Fe. Volume of the wire. What is the volume of a wire or rod? Cross section is E. Length is capital L. So the volume of a wire is L times cross section, right? L times cross section. Half, I can arrange this equation like this. F divided by A, E divided by L. So what is F divided by A, E divided by L? Those are just two words, right? We discussed that at the last class. So this is stress, tensile stress, and this is tensile strain. Tensile stress and strain times half. So you can find elastic potential energy in a unit volume. So that is this much. Okay, take it down. Take it down, and if you are done, send me thumbs up. Okay, so what is the units of E dash? E dash units. So units should be elastic energy is measured in joules, volume is cubic meters, right? So joules per cubic meter should be the units of elastic potential energy per unit volume. Write that down. E dash units is joules per cubic meter. Under that, write a sentence: area between graph and strain axis, graph and strain axis, graph and strain axis gives the elastic potential energy, in a unit volume, gives the elastic potential energy in a unit volume. Okay, so this is what it means, right? We studied this graph. So this is strain. E means extension, L is the length of the wire. So that property is called strain. Then we have stress, force divided by cross section, that is stress. The area of this graph gives us that. So you can flip this one, right? You can put E over L here and F over A here, it doesn't matter. But the area of the graph should be always with the strain axis. So this area gives us the unit volume. Sorry, unit energy in a unit volume. Energy in a unit volume. So this value is F over A and this value is E over L. So let's find the area of this graph. Since it is a triangle half, this length F over A, this length E over L. See that? So these two equations are the same, right? So what can we understand from this? In a force extension graph, we get the energy. We get the potential energy from a force extension graph. From a stress strain graph, we get the energy per unit volume. Understand the difference, right? From this graph, we get an energy per unit volume of the material that the wire is made of. But from a force extension graph, we directly get the energy, amount of joules. Okay, amount of joules. Okay, write this stuff. Take this down. Right. There's a one more theory part, right? There's a one more theory part, and we are done with the theories. Then we'll move on to doing questions. So as we are doing questions, you have to be interactive, right? More interactive. Okay, the last theory part of this, write down topic effect of heat. Effect of heat. Write this sentence. When a rod between two walls is heated, compressive forces are applied on it. To prevent its extension. I'll explain that later, right? Just take this down first. Is applied on it to prevent its extension. So that's the first point. The second point, when a taut wire, taut means T-O-U-T, right? Taut wire is cooled. When a taut wire is cooled, tensile forces are applied on it. To prevent its compression. To prevent its compression. Okay. Right. So this theory part explains this, right? At the first sentence, we say that. So you have two walls, fixed walls. Then you place a metal rod or it can be a wire. A wire cannot be placed like this, right? Let's say this is a rod. You just slightly place it between two rigid walls. Those walls cannot be moved, right? So when you increase the temperature of this rod, what happens? When you increase the temperature of something, usually that thing expands. I think you learned that in like O levels. When you increase the temperature of something, that thing expands. Here what happens is, this is trying to expand. This rod is trying to expand, but it is not allowed. Expansion is not allowed by these two walls. So what happens? It is like these walls are pushing on this rod to keep its original length, which causes compressive forces like this. Let's say F1, that causes F1 forces, right? Let's say F. So here, that's what happens as you increase the temperature. Then let's think about the another scenario. So you have two rigid walls, but in this case, you have a wire. You have fixed a wire between these two places. Here what you do is you decrease the temperature. So what happens when you decrease the temperature? This contracts, right? This doesn't expand, this contracts. So when contraction happens, what happens? But that contraction also is prevented by these two walls. So it can be prevented. This wire is not allowed to contract, right? That is prevented by applying tensile forces on the wire. Here the wall applies tensile forces, here applies compressive forces. So that is what happens. Let's say that contraction, let's say the here it tries to expand, right? Let's say it tries to expand to this side by like delta L, but it is prevented. Delta L is also equal to extension, right? This is trying to extend that much. So delta L is equal to simple E. This is the prevented amount of extension, prevented amount, right? So we have this equation in thermal physics. If you haven't learned that, just remember this equation, right? So this extension, when you increase the temperature by a theta, you have this equation: alpha, initial length, and increase of temperature. This is just an equation in thermal physics, right? You will learn that when you learn expansion. Alpha, so we call this prevented compression. In this case, it is a prevented compression. In this case, it is a prevented contraction, right? This matches for both cases, right? So we have this equation. Then I'm going to apply the equation that involves Young's modulus. So that equation is this one, right? F stress equals Young's modulus times strain. So this is the another equation. So then what can I do is instead of E, I can apply this alpha L theta, then divide by L. Oh, sorry, it's already divided. Then just cross multiply and you can find this F. So F is equal to YA alpha theta. So this is the compressive force applied due to increase of temperature, right? You don't have to remember that. You have to remember these two fundamental equations. Then you can quickly derive this, right? You don't have to remember this. Okay, take it down, and if you have any problems, send me a message. If you want, you can write this alpha as temperature coefficient of expansion. Just the equation, right? Easy equation, you will learn that in thermal physics. Yes, the compression and tension forces, they act to opposite directions, but the magnitude, we treat them similarly, right? Those are two types of forces. But for both cases, we can apply this model. You will get the same result. But the directions are different, right? Okay. So up to now, we have discussed all the theory parts on elasticity, right? All the theory we have covered. Now what we have to do is we have to do and practice some questions. So get the tute. If you didn't get the tute, please manage with the PDF, right? Some is try the first question. First question, we'll quickly keep. We can do many questions, but you have to send me the answers in the messages, right? So we can quickly move on. First question, try that. So the stress is F over A, right? So this is the stress. Force divided by cross-sectional area. So what should be the dimensions of that? Dimensions of force MLT minus 2. Area is L squared minus 1 T minus 2. So this is the dimensions of stress. Then strain, equation for strain is E divided by L. E is a length, L is also a length. This is extension, this is initial length. So the dimensions is 1. Dimensions is 1. Then we have Young's modulus. So this is the equation for Young's modulus. This is a different form of the same equation, right? Stress equals Young modulus times strain. You know that this doesn't have any units, I mean dimensions. So the dimensions of that one is 1. So as you can see, dimensions of Young's modulus also is equal to dimensions of force divided by area. So it should have the same dimensions. Got it? Yeah, it should be the fourth one, right? Should be the fourth one. Then do the second one and quickly send me the answers as text. Send me the answer. So try the second one and send me the answer. Okay. So what they ask is derivative units of Young's modulus. Right. Kilograms per meter. We know that this Young's modulus means force divided by area. So this is like pressure, right? So this should have units of pressure. Newtons per square meter is one of the units, and joules per meter as well is one of the unit. No, sorry, not this one. Only Newtons per square meter. So the answer should be second one, right? Try third one. Try third one. And send me the answer quickly. You just have to substitute the values to this equation, right? That's all you have to do. Try third question. If you want, you can draw a sketch. Diameter is 2 millimeters. Length is 2 meters. So what they ask is Young's modulus, right? What they ask is Young's modulus. The extension also is given. Extension is not given. It is given as 1 millimeter. Extension means simply, right? It is 1 millimeter. Okay, what's the problem? What's the value? Fifth one. Okay, let's see. So the force is 5 times 10 to the power. Sorry, 5, 10 divided by area. Area means the cross section of the wire. So the this is diameter, right? So the radius should be 1 millimeter. So these have a circular cross section. So it should be 5r squared area. R squared means 1 squared times 10 to the power minus 3. You have to convert everything into meters. So when you convert it, this becomes 10 to the power minus 6. Because 10 to the power minus 3 squared minus 6 equals y. Extension 10 to the power minus 3, that is 1 millimeter into meters, divided by length. Length is 2 meters. 5 cancels off. 2 goes to here. 10 to the power 7, 10 to the power 10. Third one, right? Check that. And the units newtons per square meter. Okay. Answer is third one, right? Then try fourth one. Fourth one. Try fourth one. And send me the answer. Okay, we'll check that later, right? So this question is somewhat different, right? In this question, what they have given is change of extension. When you apply a change of, when you apply a change of, when you like, you increase the mass attached here by 5 kilogram. So what happens is, then the extension changes from by 4 millimeters. So this is change, right? Not the exact values. Whenever you get something like that, so here force has changed with, then the extension changes with that. So in this equation, these are the variables, force and extension. So not only in this case, whenever you get something like that, you can always write this. You can put a delta here to the variable. So that is delta F, and put the delta to the other side. Okay. So you can have this equation whenever they have given a change of one variable with another variable. Then you can substitute values for this. So the change of force is not 16, change of force is 5 kilogram, right? 5 kilograms means 50 Newton. You have to multiply by 10 to make it Newton. 50 Newton divided by area is 2.5. Square millimeters converted to square meters. So that is minus 6. Y. Delta E is 4 millimeters. 4 times 10 to the power minus 3 divided by length. Length is 2 meters, right? Okay. So this case you have to find Y. So what should be the answer? If you didn't get that right, take it down and let me know the answer. Right, so this is 2.5, 2, this is 5, 5 means 5 times 10, right? So this is 20. This goes here. If you want, you can cancel these two. Cancel these two. 10 to the power 7 equals minus 3y. So y is 10 to the power 10. Third one. Yeah, the answer should be third one, right? You have to put the units 10 to the power 10 newtons per square meter. That's the Young's modulus. That's the Young's modulus. Okay. Right. Then try fifth one. Fifth one also is similar. You have to use the same equation. You know, whenever there's two variables, you just have to put a delta there, right? Delta means the change. Okay. Try fifth one. If you want, you can draw a sketch. Mark all the details. Length simple L. W. Cross section A. Cross section A. So what do? We decrease the W weight to W over 2. So the change is W over 2, right? Change is W over 2. In this case, what happens is extension also decreases. How much? This is change of extension, right? Not extension, change of extension is L over 10. Decreased by L over 10. Okay. So what's the answer? We are saying about change, right? Not a one state. So you have to put a delta here and a delta here. Then you do the substitution, that's all. So you have to understand a question like third question and these questions, right? In the third question, it is not a change of states. In this question, it is a change. Okay, tell me the answer. Okay, so the change of force is delta W, right? Sorry, not delta W. W divided by 2, that's a change here. Area is A, Y. Change of length is L over 10. Both lengths are the same, right? LL cancels off. So Y over 10 equals W to A. So what do they ask? A Young's modulus. 2 cancels off 5, 5W over A. Did you get the answer? So this is the exam question, right? The answer is third one. Right. Then try sixth question. Sixth question. So they say the maximum stress without breaking 10 to the power 6 newtons per square meter. The density is given. Okay. Density is given. So this is a wire with, this is not a light wire. This is a wire with weight, mass, right? Earlier we always talked about light wires, right? But this is here we cannot neglect the weight of that. self weight. This has self weight. So we know that the maximum tension of a wire is at the top, right? It's at the top. Here the tension is 0, and tension gradually increases as you go up. So you have to think about this one, this point, tension at this point. So the tension at that point, if you think about this whole wire, is equal to the weight of the wire. That is the self weight of the wire. F of A is given, right? This is the maximum stress. This is dependent on the material. This is dependent on the material. So from this one you can find the maximum F the wire can bear. Put A here, 10 to the power 6. Cross section, is it not given? No, it is not given. A is the cross section. So what they ask is the length of the wire. So this is the F max. So how can we write the weight of the wire here? Weight of the wire is volume of the wire. Volume is cross section times length. Cross section times length, it is the volume, times density is the mass of the wire. Then multiply that by G. Then you get the weight of the wire. Right? So this W is equal to F max. Substitute this whole thing here. If you don't understand, tell me. Okay. So this is the F max. That's the maximum weight of the wire. A cancels off. Length is what they ask. 2500. 10 equals 10 to the power 6. 10 to the power 3. 1000 divided by 25, that is 40 meters. 40 meters, right? Clear? So 40 meters is the maximum length that wire can have. If you have a higher, the wire would break from here. Wire starts to break from here because highest tension of a wire due to its self weight is at the top, right? This point holds the whole wire. So the highest tension is at the top of the wire, right? Got it? If you have doubts, send me a message. Right? Then do seventh question. These are mechanics, right? So if you understand mechanics, these are not that hard questions. Only difference is you just have to apply that Young equation with Young's modulus. That's the only difference. No, AL rho G is, yeah, we can apply that here. This is not only for hydrostatic. A means cross section, L means length. Cross section times length is volume of the wire. So we know that, right? So the mass is equal to what? Density times volume. This is density times AL is the volume. Then to make it a weight, you have to multiply that by G. Yeah. So in that way you can find the length of the wire. Okay, that question is involved with circular motion, right? So you have a rod or can be a wire, it doesn't matter. So we are rotating it in a vertical motion. You know that due to the vertical motion, what happens is, in order to create the centripetal force, you know that you need a centripetal force to have a circular motion, right? In order to have that centripetal force, this end, there's an object here which has a 15 kilogram weight mass. This end extends. This end extends, right? So what they ask is the extension at that end. They ask extension of this end. Length is 0.5 meters. Cross-sectional area 0.02. So square centimeters 10 to the power minus 2, minus 4, because it's squared. Frequency is 2 Hertz. Frequency means, you know frequency? 1 over T. T is 1 over F. So it takes 0.5 seconds to complete one round, right? So what they ask is extension of wire when the object is at the lowest position. These are just mechanics questions, right? Nothing more. So that's why we say, like, if you know mechanics well, you know any part in the whole syllabus, right? There has nothing new after that. Okay, here the forces acting, tension upwards. There's a tension acting upwards, and there's a weight acting downwards. What you have to do whenever you have a circular motion question, you always have to apply F equals ma towards the center, right? So I'm applying F equals ma towards the center. Okay, tension upwards minus mg equals m. Acceleration is centripetal acceleration, which is r omega squared. So tension is equal to mg plus mr omega squared. So you need to have a value to this one. So mg is 150 Newton plus mass is 15 kilogram. Radius is 0.5. Omega. So how can we find omega? So you know omega is equal to what? 2 phi divided by time period. Omega is equal to 2 phi divided by time period. Time period is 0.5, right? Which is 1 over 2. It goes to up. Becomes 4 phi. 2 phi divided by 1 over 2. 2 goes up. So omega is 4 pi. Omega is 4 pi rad per second, which you can substitute here. So 4 phi squared, omega squared. So 150 plus 15 times 0.5 is 1 over 2. 4 squared is 16 times 5 squared. Since this is an MCQ, right? You can do an approximation to get the answer. You know that 5 squared is equal to 10. It's actually 9 point something, but you can take it to be equal to 10, right? Because this is MCQ. Otherwise, you have to apply 22 over 7. So 5 squared is equal to 10. 8 times 15 is 120. 120 times 10. So 1200, 150, 0, 5, 3, 1. 1350 Newton. That is the tension inside the rod or the wire. First you have to find that. Then in order to find what they ask is extension, right? Then you have to go for the Young's modulus equation. So what can we do? F L over A divided by Y is equal to E. This F is tension. That is the force inside this rod, right? 1350, length is 0.5. Cross section is how much? 0.02, 10 to the power minus 4. Y is given as 2 times 10 to the power 11. This much should be the answer. So this is not a complicated question if you understand the mechanics and all that, right? So you just, all we had this, we just applied F equals ma towards the center and the other equation. Then simplify that, take it down and simplify that and get the answer. Okay, the answer should be 1.1. Now is it okay? Right, so the answer should be 1.6 something, right? 1.672 millimeters. Due to this circular motion, it extends by 1.672. Okay. No, you don't have to add e to the radius, right? Because that's a very small value compared to 0.5 meters. You will get an answer, but you will get a very close answer still, right? It doesn't make that much of a difference. But there are some cases you have to think about e. There are some cases depending on the values, right? Right. Then try this equation, not the equation, question 21 question 21 and send me the answer. So what they ask is, according to that graph, they're asking about Young's modulus, right? They have given a stress strain graph. So this is up to this is we call proportional limit. This we call proportional limit. That equation only is valid up to the proportional limit. After that, it is not valid, right? After that, it is not valid. It is only valid up to proportional limit. After that, this graph goes like this. You cannot apply equations after that. So what is the Young's modulus? So to this point, just apply that equation. Then you can get the answer. Why? So Young's modulus is actually stress divided by strain. So these values are given, stress and strain. 16 times 10 to the power 7, right? 7 divided by strain is 10 to the power minus 4. So the answer should be 16 times 10 to the power 11 newtons per square meter. If you have any doubts, send me a message. You cannot do this after this point. You can do that to this point or before that point, right? After that you cannot do, because these are not proportional, right? Yeah, because you can only apply this equation f over a is y e over l. You have applied a constant here, I mean gradient of this graph. Y is the gradient. Gradient should be a constant, but after that gradient is not constant, right? It is this called proportional limit. You can check with that the last class recordings, right? Then try 22. Next question. So what they ask is a true question, sentence about above graph. Y obeys Hooke's law. So what is Hooke's law? F proportional to extension, right? That is the Hooke's law. All you have done here is you just have divided by constants, initial length and areas, right? That's the only difference. Y obeys Hooke's law only between O and A. Yeah, Hooke's, that is why it is proportional, that is why it is linear. It follows the Hooke's law. After that, extending is easier, right? See that? When you apply this, let's say this amount of a force, extension is too much. After this point, it is easier to extend. It is practically also is viable, right? Like when you have a wire and you keep strengthening it, not strengthening, I mean extending it. Once it reaches the proportional limit, that wire gets thinner, right? Wire gets thinner and it is trying to break. After that, it is easy to extend. It is not hard, it is easy to extend after A. Yeah. So the answer option should be third one, okay? If you don't understand, tell me. Option should be third one. From here to here, it obeys the Hooke's law. After this point, what happens? Doesn't obey the Hooke's law, but the extension is easier. Extension is easy. It doesn't require this much of a force to have a certain amount of extension. Extension is easier. Okay. Yeah, both are same, right? Like F equals F proportional to E. That one and this equation same. Not same, I mean similar. All they have done is divided by A and capital L. These are constants for a given wire. A and L constants for a given wire. Okay, A and L constant for a given wire. Right. Then try 37. 37. First draw the sketch. So you know these two rods. is a parallel system, right? Parallel system. So this rod applies a force F1 upwards, and let's say this applies a F2 upwards. You have to think about the equilibrium of the this one. I think it is a pillar or something. No. Concrete beam. So the concrete beam is balanced by these two forces, F1 and F2. Okay. So due to the weight of that, these two pillars compressed by the same amount. They say it remains horizontal, so compressed E, this also compressed by E. Right? So what they ask is this X. So what did I tell you? Whenever they ask like a length involving forces, you always have to go for moments. Right? Moments. Force times normal distance, perpendicular distance. So I'll consider the equilibrium of the pillar. I'll take the equilibrium of around G, since I need to get rid of this W, right? Okay, so to this side, F1 times X. F1 times X. Other side minus F2. This distance is what? This is L. L minus X. So this whole thing is equal to 0 because in equilibrium, right? Again, you have F1 divided by F2 equals L minus X divided by X. So these forces, these are compressive forces built in each pillar. So for this one, you just have to apply that Young's modulus equation. So what's the equation? F over A, I'll put A to the other side, YA E divided by L. F divided by A put to the other side. So when you think about these two pillars, right, you don't have to keep writing stuff, right? When you compare these two pillars, remove all the constants. So what are the constants when we compare these two? They are made of the same material. So Y is a constant. Don't write that. L is a constant. Not this L, height of the pillars is a constant. Extension also is constant. Not extension, compression also, it's compressed by the same amount. So from this equation, what can you write? F is proportional to A. This is all you have to know. Right? So instead of F here, you can put A. Or else I can separately find that F divided by F2 is equal to A1 divided by A2. So A1 is this one, that is equal to A squared. F2 is this one, 5 A squared over 4. A cancels off. So the ratio is 4 divided by 5. L minus X divided by X. Then you have to find X. You have to subject X after that. Right? This will be like a very complicated equation if you write all these terms. Don't write unnecessary stuff, right? That's why things get complicated. If these are same for both, you know that when we divide the same thing, they get cancelled off, right? So don't write. So this ratio is equal to 4, 5. Then cross multiply 4x equal 5L minus 5x. Take this to the other side, 4x plus 5x equals 5L. Take x out, 4 plus 5 equals 5L. Then cross multiply again, x is equal to 5L divided by 4 plus 5. Right? If you didn't understand anything, ask me. Ratio of area. This is a square cross section. This is a circular cross section, right? So for the circular cross section, this is square cross section. Area is a squared, a times a. For a circular cross section, 5 times. They say that simple a is diameter, so radius should be a over 2. So this becomes 5a squared over 4. So a1 here is a squared divided by 5a squared over 4. Then a squared cancel off, 4 goes to the numerator, 5 goes to the denominator. So is that the problem? Okay. So what we need is this ratio, right? F1 divided by F2. So we have this equation. F divided by A is Y times E divided by L. I put A to the other side. I'll write that like this. So what happens if you write F1? For both cases, they are made of the same material and the compression is same, length also is same when you compare two. Okay, so you write this equation for this pillar first, y e divided by L. You can write it as A1 here. Then for the another pillar you can write it as y e over L A2. When you divide it, what happens? Division is equal to A1 divided by A2. Because all these terms cancel off. Because they are the same for both pillars. Did you get it? Okay. So you don't, this is an MCQ. Even in essay you can do that. When you have to compare two things like that, don't keep writing constants, right? You can neglect constant, but make sure those are constants, right? So it's going to save a lot of time there. Okay. So you have to use proportionalities. After that, try 30, 36. First draw is sketch. Try 36. I think the question is not clear, right? We'll skip that question 36 because there's a problem with that question, right? Okay, we'll try 38. We'll try 38. Just you can cut it off 36 question, right? There's a problem with that question, right? So rubber strip, we have a rubber strip, 15 centimeter length. Then it is pulled down by a force 0.4 newtons. Its length becomes 27 centimeters. So when you apply 0.4 newton, it increases its length, become 27 centimeters. Length of rubber tube where it is pulled with a force, then you apply 0.7 newton. So what they ask is what could be the length of the rubber strip. Okay. So this 15 centimeter is without any force. 15 centimeter is without any force. Here what is the extension? 27 minus 15, so that is 12 centimeter extension. Force applied is 0.47. You don't need, you can apply this one as well, right? KE. You don't need that whole equation, okay? Here the force applied is 0.4 equals K times E's extension is 12 centimeters. In this case, force applied is 0.7. K does not change, it is a constant for both wires. Extension is what they ask. So you just have to divide those two equations, right? So 0.4 equals K times 12. If you divide it, you get 0.7 divided by 0.4. 3, 0.1, 7 times 3, 21. Okay, you get 21 centimeters. That's the extension. What's the initial length? 15 centimeters. 36 centimeters. Third one, yeah. Third one. Okay, try next one. 39. Try 39. If you have any questions, send me a message. Try 39. Natural length means length without applying any force. So at the next case, length is increases 30, extension is 42. You have to add that to the initial length 30 centimeters, so you get 72 centimeters. Yeah. Yeah, it is the same equation, right? Y times E divided by L. Just put E to this side. Sorry, A to. AY divided by L equals E. So this term is K, right? Spring constant. It's the same equation actually. K is equal to AY divided by capital L. Right, then try 40. So they're asking about a work. So that work is equal to what? Stored potential energy. Not energy per unit, right? Per unit volume. It is energy. So what's the equation? Half Fe, right? To find the potential energy. This potential energy is equal to work done. Half Fe. So the force is tension T. So what's the extension? D minus L naught. So the answer should be the first one. If you have any problem with this, always refer to this graph, right? Fe graph. If they're asking about energy in a unit volume, you need a strain stress graph. This graph. But if they ask force and extension, you have to follow this graph. I think it is clear. The answer is first one. Right. Then try 41. 41. If you have any doubts, send me a message, right? Okay, try 41. Can you send me the answer if you get the answer? Or if there's any doubts, ask me, right? All you have to do is you just have to find this area. So from this equation, you can find the force required. Extension, they have given extension. Two times 11. minus 6, extension 0.1 times minus 3 divided by L. Okay, let's see. 2 cancels off, minus 5, sorry, 10 to the power 5, 10 to the power 2, 10, right? Force is, I think, 10 Newton. Okay, so half Fe, half force is 10, extension is 0.1, 10 to the power minus 3. Isn't the second one? No, not the second one. Yeah. Fourth one, right? 5 times 10 to the power minus 4 joules. So that's the fourth one. Right, then try 43. 43. Whenever you get a question like this, refer a graph. So from this equation problem, you should understand another 0.25 does not mean same energy, right? It is harder to pull another 0.25 because already there's a built up force, right? So it takes a more energy, which represented by this graph here, this large one. So you have to find area of this. That is the answer. Third one. Okay, let's see. Okay, I'll just apply the equation here, then find F here. Let's say F1. Let's find F1 times 0.25 divided by 2 is equal to 0.5 joules. So from that you can find F1. F1 is 4 Newton. So from that you can find K, spring constant. Just apply F1 equals KE. 4 equals K times E is extension 0.25. So 0.25 means 1 over 4 goes to the other side. K is equal to 16 newtons per meter. So from that you can find the F2 value. So from here to here it is 0.5. So F2 is equal to 16 means K times 0.5. So that is 8 Newton. F2 is 8 Newton. Now we know all the values required to find the area of this. Okay, let's see trapezium. 8 plus 4 divided by 2 times length is 0.25. 12 divided by 2 is 6 times, this is 1 over 4. 3 over 2, that is 1.5 joules. So the area of this one is 1.5 joules. Area of this was what? 0.5. But area of other part it is 1.5. No, you cannot do like that. First you have to apply for this one. Area of this is equal to 0.5 joules. Yeah, the force is always, you have to increase the force all the time, right? You have to increase the force all the time. The thing is, when you extend a spring, you have to apply more force if you need to keep increasing the string, extension. Okay, so the force always increases to have higher and higher extensions, right? Okay, so today we have discussed up to 43. Then you can try the other questions at home, right? There are essay questions as well at the back. There are essay questions as well. Then you can try the other questions as well. I'll discuss a few more questions at the next class. Oh yeah, I'll send that. I'll send that. You can try these questions as much as possible. I'll discuss further questions, mostly exam questions, on the next class. And if we had time, I'll start the second part of this unit, which is viscosity. Okay, which is viscosity. Probably by the next week we'll be able to finish this elasticity part from this one. Okay, so if you complete this tute, you are set for the exam, right? There's nothing more than this. And if you have any questions, you can send me as you are doing the question. I mean, as you are trying the tute. I'll further try questions. Okay. Yeah. Okay. If you have any questions, tell me. Yeah, the answer should be 2 times 10 to the power 9. Yeah. I think. Let me check that. I'll get back to you. Right. Right. Yes, sir. Complete the note. I mean, tute as much as possible. There might be you will get a complete essay question only from this part, right? As I told you earlier, this is not a that complicated lesson. You can easily score marks from this unit, right? Okay. Good night then.